maybe the technology is so early that, you know, there are flaws in it, there are bugs in it that have to be worked out. The people that are not the innovators lose confidence in it, and they go on down into this, what they call the trough of disillusionment. But then the technology begins to improve, gets easier to use, the population of users grows, we're moving from innovators to early adopters into early majority, and then as that occurs, you're going up the slope of enlightenment, and then finally when we're up to some of the laggards are also using this new technology, which is not new at this point, and now we're in the plateau of productivity. Let's look at this hype cycle in a little more detail, and this is again put out by the Gartner group, and we can see, you know, what's going on in detail as you're moving along the cycle. Okay, and this timeline down here, it could be, you know, maybe just a few months depending on what this item is, what this piece of technology is that's being targeted with this particular cycle. Okay, and you know, this generation, this might be, you know, we're talking about second generation, we're talking about full adoption. You know, we're still in the innovation and early adopter populations. You know, less than 5% of people have it at this point. Okay, here everybody's talking about it. You know, you might have, you know, 70, 80% of the potential population discussing this technology, but then they're not actually adopting it. They're looking at it, thinking about it, and then this whole group is falling down this way into this trough of disillusionment. Okay, and then as things get easier to use and improved and things move along and evolve, we're getting over here and lots of adoption is going on. Okay, now what are some barriers to use them? Let's back up into BIM and talk about contractors and subcontractors using 3D models in their projects. Okay, a lot of them. What's one barrier? They think, oh, this is, you know, I don't like this new stuff at all. I like to stick with my paper plans and drawings and perspectives, and that's the way we've always done things, and that's how we'll continue to do it because it's always worked out for us, not realizing that they may in the future become disruptive and be driven out of business. Okay, again, toward the end of this lecture, we'll get into defining what disruption and disruptive technology actually is. Okay, you've got to be aware that it was the contractors, not the architects, designers, and others, that powered the adoption of BIM and its use of 3D models. It was the contractors who were the first to see the power of the models. Okay. Another barrier to owners and others and architects not adopting BIM is that it's not required by the project, by the owners, and therefore they don't do it on their own. Okay. Many of them say, yeah, this is a good idea, we'd like to do it, but it's way too expensive, we've got to buy all this new stuff and everything. You know, they have a false impression on what it takes to get into 3D modeling and using BIM on their construction projects. Okay, they think that high-level model builders have to be hired, not realizing that current in-house people can be trained to work with the 3D models. You can quickly learn how to work with them on a entry-level basis, and it takes about a year to become super proficient with it. But it takes but a few weeks or less in order to be able to do it at a level that is usable and gets you started in the adoption process. Okay? A lot of people, a lot of companies, they're extremely busy with their current work, and they don't wish to invest in the time and putting their current personnel over into the BIM area. Okay, and they also, one of the worst barriers is they say, well, that's might be pretty stuff, but there's really no benefits to using it versus how we are doing things currently. Okay. Okay. Let's jump into constructability and buildability. Okay. Buildability, you've probably heard these two terms, and some individuals think that these terms are interchangeable, but there is a difference in the two, and we'll talk about them. Okay. Buildability is determined by the project's design. Okay. And it's the design, how do they design it? Is it designed to be more easily built than another design would be? Okay, the buildability increases as the design makes the project easier to build. And we'll get into some details of that in a moment. As you can see there, lower manpower requirements is a mark of buildability, whereas constructability is not based on the design, it's based on the project management methods, okay? And the crew productivity is what is a mark of the constructability. And if you can see a difference in project management methods that from project to project improve the crew productivity, then you've improved the constructability of the project. Okay. Again, just to reiterate, buildability is based on the design determines the buildability. The project management determines the constructability. Okay. This is just an example of the constructability factors that a specific government entity or a contractor with his in-house scoring methods uses to determine constructability. In this example, we've got three large areas that make up the constructability. We've got design attributes, construction attributes, and external impacts. Okay, the design attributes, there are 6 different areas of that. Okay, the more amount, if you look at number 1, the more amount of precast and prefabricated items, that the greater amount of those increases constructability. If you'll remember, or if you're aware of, in our last lecture, we were talking about the concept of parts in the construction industry versus the bill of materials used in manufacturing, where it is extremely well defined in manufacturing, and in construction the equivalent, the concept of what we're calling parts, is not as finely detailed and cataloged as it is in the manufacturing area. Okay, the more standardized portions in the grid layout of the design of the project, that's going to increase your constructability. Okay, how standardized are other areas of it? You know, how available is skilled labor? The construction attributes, again, we've got 1, 2, 3, 4, 5, 6. We got 8 areas there, and we've got those questions to answer. Again, those go into contributing to the degree of constructability. And then there's external impacts. Okay, are utilities easily available? Or how remote is your site? Okay, a real remote site, you may have trouble getting the needed equipment there, and therefore your constructability is less than it would be otherwise if the equipment was more easily available, and if transportation was more easily available. Okay, again, here is a sample form used by a contractor to determine the constructability score. So they go through, look at the project, fill out this form, and they get all these a certain number of points based on their observations and based on the facts of the project to develop a score. Okay. Now, constructability scores may be done by the contractor independently, because that's part of the way they take care of delivering their projects. And also there are some governments around the world who require all major projects to meet a minimum constructability score based on that country's scoring method. Okay. Again, different contractors and different requiring agencies, government agencies that require certain constructability scores, they have their own different ways of determining the score. Okay. Again, here is a sample of how one group does it. The score can run from 0 to 120, and there's 3 different areas of the scoring sheet. You can get up to 60 points based on the points that your structural system can contribute. 50 for AMEP, that's architecture, mechanical, electrical, plumbing. And then there's some bonus at the end, 10 points, based on innovation and productivity. Okay. Again, as I just mentioned, some countries have buildability standards and require a minimum constructability score for the project to proceed or even to begin. If not, it will have to be redesigned and rethought out. Okay. Now, let's talk about the Pareto, non-Pareto. This is an important tool used within VDC to help determine, what's the best design. Okay, in different parts, we'll look at some different things where we can view built up through algorithms Pareto frontiers. We'll define that all in just a minute here. Okay, but the Pareto principle is the observation that most things are not evenly distributed, that there is an unequal relationship between inputs and outputs. Okay, for example, 64% of your output at work comes from 23% of your time there. Okay, 18% of your customers provide 79% of your revenues. In a construction schedule, 7% of the activities are the causes of 96% of the delayed items. Okay, so this is telling us that you want to look at those small percentage inputs that are causing the bad things in the project, or vice versa. You want to look at those little things such as the investments responsible for 86% of the gains, you know, what's so good about those? Why are they so helpful? Okay, so we can use the Pareto principle and the observations from it to determine what's really important, what deserves the resources and the time and the effort to minimize bad things to maximize good things. Okay, the name Pareto and Pareto principle, it derived from an Italian economist in 1906, Vilfredo Pareto, and he noticed that over and over and over out in his garden, 80% of the peas were produced by 20% of the plants. You'll also hear the Pareto principle referred to as the 80-20 rule. Okay, but the way we're looking at it, it's those numbers don't really mean anything because those percentages can vary greatly. You know, like 24 to 60 or 12 to 92 or whatever, based on whatever we're looking at. Okay, but making a good Pareto observation allows you to focus, like we said earlier, on minimizing the things that are causing the greatest trouble and maximizing the small things that are causing good things for you. Okay. Again, we just discussed all that. Let's look at some graphs. Okay, and let's understand the idea of the Pareto frontier. Okay, these are three graphs here, and they're all based on, these are all two-dimensional. So there's two, call them, hang on. There's two items we want to look at in these three graphs. Okay. And we want to use the best thing, and we review these graphs produced by algorithms to see what is our optimal choice in whatever it is we're observing. So over here in this graph with the green things, each dot in it is an alternate design. Okay, and anything that's not on this frontier, not a red dot, that is not optimal. Whereas anything that's on the frontier is optimal based on your decision on whether you want to, you know, take this much risk, get this much return. You know, here we're increasing the return a lot and increasing the risk just a little. Whereas as we move up here on the curve, you can observe, even though these are on the frontier, they're optimal. Up in this area of the graph, we're increasing risk faster than we're increasing expected return. Okay, so somebody would want to make a decision by picking something somewhere along here. Okay. Any green thing is not optimal. You don't want to pick one of those alternatives. Okay, so you had a design alternative here. Again, the purple line is the Pareto frontier. Okay, any blue dot, you don't want to pick it. Okay, you would want to pick something along here. Okay, same thing in this curve here. This is your curve, your optimal curve. Anything on the curve is optimal. It's up to you as you review these alternatives to determine which of these design factors or input factors, you know, where do you want to balance this? Okay. In the 1700s, back in, you know, Isaac Newton and Leibniz time, there were numerical optimization methods. And they could do it that way. Not until the 1970s, so that's you know, 270 years, 200 years, did a different type of optimization methods begin to be developed, okay, and they were CAD-based. Then beginning in the 1980s, that's when multidisciplinary design optimization was developed, and there's different methods of achieving that, okay? Now, let's look at the algorithms, or the idea of the algorithms, and input from design groups, okay? We've got an algorithm here. We're putting the mathematical inputs into it, and we've got different discipline groups, different subcontractors, engineers, designers, and whatnot over here, and they're all in one team. We'll call this team E7. They are simultaneously putting in input and working with the algorithm and getting the output, which gives us, again, there's the example of our graph that has the Pareto frontier on it, okay? The reason this can improve the quality of your designs and improve the cost and reduce waste in the construction project is if you were doing the design in a sequential manner, one individual, let's say the steel designers, do the steel without any input from the HVAC, any input from the concrete people or the drywall subcontractors, the plumbing, the electrical, and they just pass it on down the line, then whoever's further, as you move down the line, they're kind of stuck because all this other stuff prior to that has already been done, and they've got to work within the constraints of what they've been given, okay? Here's some examples of that, of working with the MDO processes, okay? Let's look at number one. There's an HVAC team, and their goal is to develop the optimal ductwork sizes for this project, okay? Now, we've got different groups. We've got 5 different groups contributing or making up this team and contributing toward the design. So they're all providing information that will eventually determine the optimal ductwork sizes, again, given a MDO Pareto algorithm. Okay, here we've got the HVAC engineers, the ductwork manufacturer, the equipment manufacturer, the structural designers. Okay, now we're working with the ductwork. We know where the steel's going to be, or we know if we need to move some of the steel structural members, and they're all working together, coming up with the goal of determining optimal ductwork sizes. Okay, the goal here is, this is our structural frame team. That consists not just of structural engineers, but also the erector, that's the subcontractor putting the steel up, the rolling mill that will produce the steel, and the transportation group that will get the steel from the mill to the project. Okay, they're all working together, determining what types of members and what sizes need to be part of this project. Okay, do we need I-shapes here or not, or maybe joist girders, maybe built-up girders, whatever. Okay, again, these people are all putting in input, and we're determining that Pareto frontier to help optimize the structural frame of the project. Okay, again, we've got the foundation team, we've got the earthwork team, and they're all, you got various groups of different kind of people contributing to determining what is the best excavation equipment. It's not just the general contractor saying, here, we got this and this and this piece of equipment, that's what we're going to use on this job. Okay, these people are going at it at a better way. Okay, they're all putting in input, we're producing a Pareto frontier, and then we're reviewing that, and that's given the group the best idea for the best choice at the best price as to what to have on that project. Okay? An MDO model, we're trying to maximize or minimize the function j of x, and we want the value of x that gives us the best j. J is our objective, and all these other inputs, all these vectors, are going to go into the algorithm that's developed, and you can produce lots of output than you would be able to do manually. You know, just producing, 5 or 6 different alternative designs, whereas when you're using an algorithm through MDO, you can produce thousands and thousands, and then determine, again, with the Pareto principle, what's on the frontier. Here's some examples of 3D Pareto frontiers. In 2D, you only have you have 2 design variables, as we saw earlier on those 2-dimensional charts. Here we've got 3 design variables, and they're producing a surface. Okay, so anything that falls on the surface, that's the frontier. When there's a 3D, or you've got 3 design variables. Now you can have as many design variables input as you want. You can have 4, 5, 60, 104. However, those are going to produce just numbers. You would need to know how to read the numbers there, because we only live in a 3-dimensional world. So you couldn't visualize that, but you could become comfortable with understanding the numbers put out, making Pareto frontiers with, 52 different design variables. But anyway, you can visually see and understand the 2D and the 3D frontiers as curves and surfaces. Okay, let's talk about VDC and the components that make it up. Okay, virtual design and construction has 4 different large areas that we can separate it into. There's process management, there's BIM. Again, we'll look at a little image in a moment to help you understand where BIM fits into VDC. Okay, the terms BIM and VDC are not interchangeable, and we defined that in session 1 of these lectures, and went into that, but I'll go over it again slightly here in a moment. Okay, we'll talk about ICE sessions. Those are real important parts of VDC and VDC methods. ICE in this case stands for Integrated Concurrent Engineering. Okay, and these are extreme collaboration sessions, and such as with those design groups we saw earlier, where you have people from many different disciplines being part of the group and coming up with a solution to an item, a concern, or design on the project. Okay, and then metrics. Metrics is just the measurement of various things on the project, and using that information to make good decisions and improve the project outcomes. Make it finish on time, improve the time that it would be if you were not using VDC methods, and reduce the cost. Okay. Anyway, VDC, 4 different areas: process management, BIM, ICE sessions, and metrics. Okay. Again, none of this is a scale. This is just to give you an idea of how all this BIM and VDC fit into construction and construction projects. Okay. If we look at the light blue oval, that's just the entire world of construction, all over the earth. Okay. And then within the world of construction, some contractors and owners are going to be using VDC methods on their projects. So within the world of construction, we have VDC. Okay. As you saw earlier, BIM is one part of VDC. VDC consists of those other three major parts, BIM being but one portion of it. And then remember that 3D models are not all there is to BIM. So BIM contains the 3D models, and VDC contains BIM. Okay, and therefore VDC works with 3D models. But here's how all these things work together, or how they're related to one another. Okay, 3D models is not all there is to BIM, but they are a part of BIM. BIM is not synonymous with VDC, but it is a part of VDC. Okay, there's a model, highly rendered. Okay, some key things used within VDC are what we call the I sessions. We saw that earlier. They're intense, specialized sections, and they take place in I rooms. We'll talk about I rooms in a second. Okay, these I sessions, the whole idea of them with this intense collaboration is to get decisions made quickly. We'll talk, that's what down here number 4, latency is. Okay, in some cases where you're not having VDC, someone asks or contacts another individual that's to make a decision, says, yes, let me look at this stuff, I'll get back with you in 2 weeks. Whereas at the ICE session, you've got to have, you're required to have individuals there for the goals that that particular ICE session is set for in order to make decisions right there. So you want to reduce that latency from a decision-making time of 2 weeks down to 2.5 minutes. Okay, you've got in these I rooms at these ICE sessions all these tools available to you to have the information and get it done. There's 2 kinds of latency. There's response latency, and that's for receiving information. You say, okay, I need, one engineer says to this this subcontractor over here, I need such and such information. So he's not waiting 4 days for it. He's waiting 85 seconds for it. Okay, you're reducing that latency, that amount of time. And then you're also using the ICE sessions to improve the actual project construction, and you're reducing the activity time from, let's say, this specific activity on the CPM schedule. It was originally, it was a 6-day thing. We've reduced it to 4.5 days. Okay, again, we want to reduce the time it takes to get information, to get decisions made, and to achieve construction activities on the site. Okay, the term co-location is extremely important in VDC, because in these ICE sessions, the required individuals must be present face-to-face in the ICE sessions. Okay, notice that I'm telling you that ICE sessions are nothing like typical meetings. They are severe, intense, latency reduction sessions where you have the tools present, and it is required at these ICE sessions that individuals do have the ability to make the decisions that are needed. They must be present. That is, they must be co-located in the ICE sessions when they're held, for specific purposes. And you want to achieve those purposes at the ICE sessions. And then at Stanford, some time ago, they developed just an organizational tool called POP models. Okay, and we'll look at the layout of those in a minute. It's a way to organize different activities and different things to get accomplished for the project, whether it be in the design area or up into the construction, the actual construction of the project. Okay, POP stands for Product Organization Process. Product could be, depending on what we've developed this POP model matrix for, we might be working with construction materials. It might have to do with equipment, might have to do with the BIM model, it might have to do with office supplies. It could be any kind of stuff or output. Okay, organization, we're talking about humans and groups, such as subcontractors, engineers, rebar crews, designers, regulatory entities, anything, any kind of group, any kind of people, they call them actors, dealing with the project. And then the process is the physical activities needed to carry out the design and the procedures on the construction site. Okay, here's just a basic layout of a POP model. There's the POP over here on the left hand side, and then you've got objectives, choices, and predictions up here. Okay, and a further filled out POP model chart would look something like this. Again, the whole purpose of this is to help you organize certain goals you're trying to achieve on the project at the ICE sessions. Okay, let's talk about I rooms. Okay, you've heard the term big room. At RIB, we've got things that are somewhat related to that called 5D labs. But the I room has to do with VDC procedures. Okay, and I could stand for integration room, intelligent room, interactive room. Okay, you're dealing with the 3D model. Okay, this is at an ICE session within the I room. Okay, again, we talked about co-location with the project team being face-to-face. We talked about response latency, okay, for making resolutions and decisions within minutes and not within weeks, okay. And then the I room gives you a stimulating environment to achieve all these goals, okay. They're typically windowless. We'll look at some pictures of a couple of them in a moment. They usually contain seats for about 25, an ICE session trying to achieve certain goal is not going to have, 400 people in attendance, okay. It could have more than 25 people, and it might be as little as 4 people, okay. And you're going to make use of smart boards, and there's typically you'll have 3, and they each have a certain purpose, okay. People will bring information with them on their laptops, okay. So you've got an I room that's going to stimulate the achieving of these goals at these ICE sessions. And then you'll have little breakout rooms attached to the larger I room so that you can have sub-sessions where, maybe 3 of the group of, 21 people in attendance are needed for a certain little sub-portion to do, okay. These smart boards in their I rooms, typically, you're going to, for a particular goal that you're working on at a specific time in the ICE session, you'll have its POP matrix displayed on this screen. You'll have the 3D model displayed over here, and it's active. You can spin it around, look at it, investigate it, get information from it, etc., etc. And then you'll have active commentary. These smart boards, you can write on them electronically as if it were chalk and a blackboard, and these things can be saved. You can scroll them and save all the sketches and notes and comments made on it, okay? You can save them into different files, bring up bring them back up, etc. Okay. Here's an eye room. Okay. This has more than 3. It just depends on what they're doing there. You can see the individuals with their laptops present with displays up here, and everybody at this point is focusing on this guy. He's doing some kind of, presenting of information to get decisions made and get things developed. Okay, this is our eye room at Stanford. That's one of my professors right there, and they're doing some things here. Lots of computers, lots of information, lots of color displays, lots of stimulation going on. These are the smart boards I was talking about. Okay, this is one of the breakout rooms over here. Okay, and here's that same eye room that we saw right here. That's the left-hand side facing the front, and this is the right-hand side over here with a bunch of people in a session here. In this particular photograph, I was present. I happened to be sitting over here talking to these people, and they took a picture, and I got cropped. So anyway, this is the eye room at Stanford University in the civil engineering building. Okay, let's talk about BIM and scoring. And again, this is technology adoption and how great or how less contractors are making use of VDC on their projects. Okay, there is a way, as when we saw the ability to score constructability and buildability, there's a way to score VDC use on projects. Okay, if you score from 0 to 25% on the VDC score sheet, you're dubbed conventional practice. If you're between 25% and 50% of the score, you're typical. If you're above 50%, you're advanced. And everybody's heard the term best practice, okay? In VDC terminology, that's not the best it is. It's the second best. Best practice is the second best, and it's if you score between 75% and 90% on the score there. If you're between 90 and 100, now you're performing innovative practice. You're really using a high level of VDC methods on your projects. Okay, so if a certain project was making use of VDC on it and it scored 80 according to the score sheet here, it would fall in the best practice range. Okay, somebody that said, yeah, we're using BIM and VDC on this project a lot, but according to the score sheet, they got a 23%, and they thought they were, way up here. They're conventional practice. And in this, the euphemism here, conventional means bad, okay? It's not as high level as what we'll call typical. Okay. Now, we can also talk about data, moving to information, moving to knowledge, moving to wisdom. Data is just raw, unconnected numbers, okay? It exists, but that's it, okay? When you organize the data and it becomes useful, such as you've put data into a book or some kind of format where it's organized, now it's information, okay? Now somebody looks at that information and kind of learns it, sees what it is. Now they have knowledge, okay? Now the application of the knowledge leading to understanding and doing something with it, now we've achieved wisdom, okay? So we've taken this data, moved along the spectrum here to achieve wisdom, okay? That's what you're trying to do with VDC, okay? That improves your project outputs, the delivery of your project, okay? If you can take the information, gather the metrics on the project, understand what they mean in order to move to wisdom, in order to apply it and reduce latency, get better output, get the activities accomplished, do it within the money assigned. Okay, you're applying wisdom. Okay, all this existed. Okay, but it's good that it exists, but you've got to move along this line and make thoughtful judgments. Okay. In this country, there are 4 major VDC research centers at different universities. Okay. At University of Texas, they've got one in Austin, Georgia Tech in Atlanta, Carnegie Mellon in Pittsburgh, and then there's us out at Stanford in Palo Alto. Okay? And RIB is in the process of designing and erecting what they call the I-2 towers in conjunction with Georgia Tech out there. Remember, Georgia Tech is one of the 4 major research centers for VDC, and so we at RIB have a very close relationship with 2 of these, Stanford and Georgia Tech. Okay. Disruptive technology. What does that really mean? Okay. The term was first developed in 1995, and the existence of a technology isn't what causes the disruption. It's the application of it. Okay, and it doesn't happen. It's not an evil thing, but big corporations and large organizations and certain types of individuals, again, these are going to be the laggards we saw on our chasm curve. They work and they do their things real good, but they're working with what we call sustaining technologies. They improve existing things, but they're not developing new things, okay, new applications. Like back a long time ago, computers were only large things, and they looked around, they saw these little personal computers being developed and sold, and they said, well, these things can't do anything, and they had no idea that, what was coming. They continued to work with their sustaining technologies, and by increments, they got disrupted, okay? But there's much more in this, not just computers. I mean, it happened in excavators when hydraulic excavators got better and better and better, was able to be applied more and more to larger and larger projects versus excavators that work with cables and pulleys, and even before that, called steam shovels. Okay, all those older things eventually got disrupted, even though they saw the existence of these other things. They didn't realize what was happening. Even sometimes management might be unimaginative and not be technology adopters, okay? And sometimes they'll eventually, if they cannot distinguish between sustaining technologies and observing disruptive ones that are coming that haven't had any effect on them yet, they may eventually fail, okay? They've got to be able to observe and comprehend what these new things are. Therefore, that's why it's good to be a cowboy and not a farmer, even though it's absolutely necessary to have lots of farmers doing their types of things, okay? You need both, but sometimes the farmers get disrupted, okay? Okay, we are about done here, and I thought this was kind of humorous. He doesn't like the sound of disruptive. He wants to get some mildly troubling technology. Okay. Okay, Michael, I will now turn this over to you.
All right, Rex, thank you. Again, this webinar has been recorded and will appear on our YouTube page. Just go to youtube.com and search for RIB Americas, and also we'll have this information posted on our website at rib-software.us. And thanks again for your time today. We appreciate you. We're currently working on a part 4 of this webinar series where we actually show you our end-to-end enterprise solution, I2, and how it uses BIM integration and VDC concepts to help do your projects virtually, where you can manage them virtually and then see all your cost savings and run through different scenarios and things to help save you money and better your project. So we'll send you that information out. We're currently putting that part 4 together. Would also like to extend an invitation to our RIB Americas conference at the end of September in Atlanta, Georgia. We'll have that. I know Rex mentioned Georgia Tech I2 Tower project and a center for BIM and BDC. They have used our I2 software to create the I2 Tower project, like Rex mentioned earlier. They are going to be part of our RIB Americas conference. They're going to feature that I2 Tower project in the virtual construction process. That again is September 28th and 29th at the Georgia Tech Hotel and Conference Center in Atlanta, Georgia. And we welcome you to come there. You can find more information again at our website, rib-software.us. And again, we thank you for your time, and we hope everyone has a great afternoon and a good weekend ahead. Thank you so much.